Okay, so here's our last chapter of the whole chemistry year sequence. Chapter 21 is nuclear chemistry. It's one of my favorite chapters, so I hope you enjoy it also. So we're going to look at two types of nuclear reactions. The first is radioactive decay. That's the process where a nucleus will spontaneously disintegrate, and when it does, it gives off radiation. And then the other kind is nuclear bombardment, where actually a nucleus is bombarded or struck by another nucleus, and they will, different things can happen. They can either combine or they can recreate something else. So anyway, decay or bombardment. So we're going to start with decay mostly. That'll probably be most of the chapter. So what is radioactivity? It was first, of course, it's always been around, but it was first discovered in 1896 as something that is out there. Henry Becquerel. He worked with uranium salts, and he was able to see that it gave off some sort of radiation. I think it had to do with photographic plates or something like that. And so later on, this radiation was shown to be smaller particles, and that you could separate them with a magnetic field, and so there were different charges on these particles. The three main types of radioactivity, there's actually more than this, but the first three we're going to talk about are alpha, beta, and gamma. So alpha rays, the first one, is bend away from positive plates, so they are positively charged. And so alpha particles are actually helium nuclei. Remember, helium has two protons and 2 neutrons. So it has a total mass of 4. That's where the 4 comes from. So 2 protons making it helium and 2 neutrons making it a total mass number of 4. And it's actually been stripped of its electrons, so it's a +2 because there's 2 protons and no electrons. Beta rays or beta particles bend oppositely from alpha particles, and so they are negatively charged. It's known that beta particles are actually high-speed electrons that aren't part of a molecule or atom. And then gamma rays are unaffected by electric and magnetic fields, so they're actually neutral. So they're similar to X-rays, but higher energy and shorter in wavelength, but they are not charged. Okay, so here's just kind of showing them. Uranium gives off different radiation, goes through some kind of a electrical plates that are charged, and so you can see that the beta particles are attracted to the positive, so that means they're negative. The gamma rays came straight through, so they're neutral, and then the alpha rays are more are attracted to the negative, so they are positively charged. So we'll talk more about them in a minute. All right, a nuclear equation now. So what's happening with nuclear reactions is that protons and neutrons are changing, and so we have to represent that. So a nuclear equation is just a symbolic representation of a nuclear reaction, and we use nuclide symbols. So remember what a nuclide symbol is. A nuclide symbol, so this is uranium-238. It's been a long time. We talk about this way at the beginning of the semester, or beginning of the year, and now here at the end. So remember that the bottom number is the number of protons, or the atomic number. So uranium is element number 92. It has 92 protons. Remember that the top number is the mass number, and it's equal to protons plus neutrons. And then obviously uranium is the symbol for it. So in this case, because there's 92 protons, so we would take 238 minus 92. What is that? 146 neutrons. So this particle will have 92 protons and 146 neutrons for a total mass number of 238. Of course, there's different nuclides, different isotopes that have different numbers of neutrons. All the same element will have the same number of protons and a different number of neutrons. So anyway, here's my mass number, atomic number. Okay, so a nuclear equation or is just writing all of the nuclear reaction using these nuclide symbols. So this is another example. This is an example of a nuclear equation. This is the radioactive decay of uranium-238. It happens to be an alpha particle emission, which we just got through saying is a helium nucleus. And so remember, here's how we write it. Helium is the element. It's got 2 protons and it's got 2 neutrons, so a total of 4. And then so that's what an alpha particle looks like. So notice that uranium has decayed. One of the products is the alpha particle, which we can represent like this, so it helps us see what's happening. And then we have another product, so that the helium atom or the helium nucleus is actually broken off, and so you can see what's left over is thorium-234. So we've actually lost 2 protons and 2 neutrons from the uranium, and we'll talk about this again in a minute, but notice that the number has gone down by 4 because it's lost 4 total protons and neutrons, and the bottom number has gone down by 2 because it's lost 2 protons. So and of course 90 and thorium go together. Thorium is element number 90. So this is actually, uranium is becoming thorium. So that's what a nuclear decay or radiation is it changing elements? At least sometimes it's changing elements sometimes. So again, we're going to have the reactants and the products represented by their nuclide symbols, and then let's just kind of go down the list of some other particles and how they're represented, because they're not all obvious. A proton can be represented like this. So obviously a proton has 1 proton. A hydrogen atom has 1 proton and no neutrons, so that's why the 1, 1. So the number of protons is 1, the number of neutrons is 0, and so the total protons plus neutrons is 1. You might also see it represented that way with the 1, 1 and a proton. I'm going to erase this so it doesn't get confusing. Okay, we can represent a neutron like this. Obviously a neutron has no protons and 1 neutron, so it looks like that. An electron or a beta particle can be written like this. So either with the E to represent electron or the beta symbol because it's a beta particle. Notice that the top is 0 because there's no protons or neutrons. And then I know it feels weird, but you'll see in a minute why we use a -1 here for an electron. It actually gets rid of a proton, and so it's a -1 there. So that's how we represent a beta particle or an electron. A positron is a particle that is the same size as an electron, but it is positively charged, and so it has the symbol, looks just like that. Obviously it's not a proton, but it does have a 1 at the bottom, and so that's how we represent it. A gamma photon has no mass at all because it's not really a particle, and so it's energy, and so it's a 0, 0. And we already said that an alpha particle is usually written like this with the helium, 2 protons and a total of 4 protons and neutrons, so 2 neutrons, 2 protons. Sometimes you'll also see it represented like this with the alpha symbol, and so either one of these, interchangeable, it doesn't matter. Same thing with beta or alpha. You can write any of those, or the proton as a matter of fact. So these are interchangeable, so you probably should know them both. I don't care which one you use, but they may both show up. So all right, And the important thing to remember is that the total charge is conserved during the nuclear reaction. So that's what I was talking about a minute ago, is that the numbers have to add up. So the sum of the subscripts should be equal on both sides of the equation. So everything to the left of the arrow should add up to equal everything on the right side of the arrow, the subscripts. And then the same thing for the super. So the total number of nucleons have to be the same, whether it's protons or neutrons or whatever. So the superscripts also have to add up. So everything on the left-hand side of the arrow has to add up to equal everything on the right-hand side of the arrow. So a lot of times the way you're going to be given a equation is that you'll know everything but one particle, and you'll have to figure out what that particle is. Although you're also going to have to write alpha and beta decay, which is pretty easy because you know that either it's an alpha particle or a beta particle coming off. So anyway, we'll do a few of these in a minute. All right, so technetium is a radioactive isotope, technetium-99. Each nucleus decays by emitting a beta particle. So what is the other product besides the beta, or what is the product nucleus? I'm going to write it here before, well, this is how I would do it. So I'll probably erase it then and bring my PowerPoint up. But I'm going to say, okay, technetium, got to look at my periodic table and see technetium is element 43, so it has 43 protons. And then of course the total mass number is 99, so we could do a quick math. It's got 43 protons and 56 neutrons. We don't need to know that, but just in case. So the 43 plus 56 is 99. Now it's going to decay to give us a beta particle. So a beta particle has this nuclide symbol, a -1 here and a 0 on top. And so what will the other product be? What will this be over here? So remember, and I always like to kind of draw a little line there where my arrow is so I remember. So the total on the left-hand side, we only have the bottom number is 43. So the total of the bottom numbers on the right-hand side has to be 43. So note, this is a little tricky. The bottom number for this has to be 44 because 44 plus a -1 will give me 43. The top number, that's easy because what plus 0 equals 99? It has to be 99. So now I look and see what is element 44. Element 44 is ruthenium. So notice that the element changes because it has to line up with what this number is. So this is ruthenium. So that's how I would write this equation. Let's see, I'm going to erase my little drawings here, and I'll work through it again just so you can see it. So yeah, so here we set up the nuclear equation. You can see technetium 4399. Beta particle is one of the products. And so what is the other product? So we have to identify what is A, what is X, and what is Z. So like I just did, if you look at all the superscripts, A has to be whatever makes 0 equal to 99, so A has to be 99. What about Z? Z has to be whatever will make Z plus a -1 equal to 43, and so Z has to be 44. And then you have to look up what is element 44. Element 44 is ruthenium, and so X changes to ruthenium. So sometimes, just before I move on, sometimes you'll see more than one product, and so if it's an alpha particle or a beta particle, you should be able to do those from scratch, but otherwise you'll have a equation that may have like a blank where it says, okay, what's this other product? Because it might be more than one. I think I've got some more examples as we go along. Okay, so why are atoms radioactive? Well, it all comes from the nucleus. What makes a nucleus stable? Most nuclei, well, not most, but many nuclei are stable. They have the correct number of protons to neutron ratio. If there's more than one proton, those protons are held together by a nuclear force. Of course, all protons are positive, and so we have to have the neutrons in there to kind of, because the positive charges are all going to repel each other, so that's what's holding it together is the nuclear force. It's a strong force of attraction between these nucleons, the protons and neutrons, that acts only at very short distances. And so this force will compensate the repulsion. So remember, all these protons are positive, and so they kind of want to repel each other, but this nuclear force holds them together. And if it's the right balance, it's a stable nucleus. But if the number of protons and neutrons are not in a good ratio, then it's not going to be as stable. So several factors contribute to this stability. The shell model of the nucleus, similar to how we talked about electrons. There's 2 electrons in the first, and 8, and then 18, and so forth. Well, there's also kind of a shell model of nucleus, and we don't need to know this nearly as carefully as the electrons, but it seems that there are certain numbers of protons that are actually more stable than others. It's experimentally found that nuclei with certain numbers of protons and neutrons tend to be more stable than others. These numbers are called magic numbers, and so it's the number of particles that complete a shell of protons or neutrons. It's probably not as much known about this as the electrons, or at least not anything we're going to focus on, so you don't really need to remember those numbers or anything, but just keep in mind that that's what makes something more stable. So these numbers are not always the same as electrons, 2, 8, 18, although some of them are. 2, 8, 20, 28, 50, and 82 all seem to have to be very stable number of protons. Doesn't mean the others aren't stable, but these happen to be. And neutrons also have some magic numbers, so these tend to be really, number of neutrons also happen to be very stable. So you can see a special stability of helium because it has 2 protons and 2 neutrons, so that's a magic number, 2 magic numbers. And another thing to note is that 82 is kind of the magic number for protons. 82 is lead, and so actually all elements that have a number of protons greater than 82 generally have decay until they get down to 82. Again, these are just, you don't need to memorize these, and these are just to give you some idea that there are some things that are more stable than others. Another thing is the number of stable isotopes generally have an even number of protons and an even number of neutrons. So if it's an odd number, it tends to be less stable. And all this is showing you is that out of all the 59% of all the stable isotopes have both an even number of protons and an even number of neutrons. About 20% of all stable isotopes have an even number of protons and an odd number of neutrons. A little less than that, about 19%, have odd number of protons, even number of neutrons, and then only about 1% of all the isotopes have both odd protons and neutrons. So that doesn't really tell us everything, but there are some that are more stable than others. And then we can also look at what's called the band of stability. And so if you plot every stable nuclide on a graph and you put the protons on the x-axis and the neutrons on the y-axis, you can see a band of stability. It's on the next slide. So this is a region where most stable nuclides lie. If they're outside of this region, they tend to be unstable. So here's what that looks like. So you can see here, this red line right here is where protons equal neutrons. And you probably have noticed before, if you start with the really small elements, they tend to be like oxygen has 6 protons and 6 neutrons. Carbon has 6 protons and 6 neutrons. Oxygen has 8 protons and 8 neutrons. Nitrogen tends to have 7 protons and 7 neutrons, and so forth. So some of the smaller elements, the protons and neutrons are the same, and you can see that this red line here, all the down at the bottom here, the stable elements, which are all these black dots, tend to be protons equal neutrons, but as it gets bigger and bigger and bigger, you can see that it veers off up this way, so that there tend to be more neutrons for every proton for a stable nuclei. So in this yellow band are all the stable nuclides, and so we know with the bigger ones we need more neutrons to kind of protect the protons from each other. So it kind of veers off away from this proton equal neutron line. But that's the band of stability. And we'll talk about it in a little while. But if a element nucleus kind of lies off to the left of this band of stability, it tends to undergo beta emission. If it lies to the right, it tends to undergo electron capture or positron emission, which we'll talk about later. And then usually it's the big elements that give off alpha emission. So again, we'll talk about that in a little while. So as we saw, if you have, like I was saying, if you have nuclides up to about Z equals 20, meaning atomic number equals 20, then the neutron to proton ratio tends to be around 1. So that's where we're saying carbon 6 protons, 6 neutrons, oxygen 8 protons, 8 neutrons. But then as Z gets bigger, as the number of protons increases, eventually you get to about a ratio of 1.5. The more protons you have, the more repulsions you have, the harder it is for them to stick together, and the more neutrons you need to offset the repulsions. And then finally, we don't have any stable nuclides with atomic numbers greater than 83. That's kind of funny because there was 82 was the magic number, but anyway, it's 83 can be stable, but anything above that is not stable. So at that point, the proton to proton repulsions become too great. So on the other hand, all elements that have an atomic number or a number of protons of 83 or less have at least 1 or more stable nuclides. The exception is technetium. Technetium does not have any stable nuclides, and promethium does not have any either. But every other element has at least 1 stable nuclide below 83.